Okay, we're going to start again for the last session of the afternoon with Mark Graham on IPFIX based detection. You have the floor.
Okay, so yeah, we're into the last session, and I don't want to disappoint everybody, but I have no IDA Pro, I have no DGA, I have no mobile botnets, I have a tiny little bit about DNS, but I have a lot about network management protocols. So what I'm going to talk to you today is about a testbed that we've been building to see whether network management protocols can have any reasonable impact on botnet detection. So a quick summary of what we're going to talk about. I'll outline the research problem that we've been looking at. We're looking at cloud provider networks. I'll explain why in a moment. I'm going to talk quite a little bit about IPFIX and flow. Hands up, who's heard of IPFIX? Okay, good. That's more than I was expecting. Okay, hands up if you heard of NetFlow. Yeah, good. Okay, lots of people. Okay. So we'll talk about the differences there. We'll talk a little bit about the build environment that we've created. Then I'll talk to you about some of the results that we've started to get, and providing there's time at the end, we'll talk about some conclusions. So I'm a PhD student at Anglia-Ruskin University in Cambridge. I'm just about to enter my final year, so it's all getting very exciting for me. And I'm studying botnet detection within virtual environments. So this is a talk really about some of the work we're doing and how that fits into some of the bigger plans at Anglia-Ruskin University. So the problem, botnet detection within cloud service provider networks. So just to be clear before we start, I'm talking about cloud service providers such as Amazon AWS. So we're talking about infrastructure as a service, platform as a service, software as a service. I'm not talking about internet service providers. You guys have already got great DNS tools that you use for botnet takedown. I'm not going to talk about that. I'm going to talk about what we could possibly do for cloud service providers. So why do we even want to look at cloud service provider environments? What's so special about these? Well, yeah, we're all being told that we're about to start down this journey down the Internet of Things, or the Internet of Vulnerabilities, as it's probably going to turn out to be called. But for the Internet of Things, we're going to need somewhere to store our data that's central, that we can easily receive it, and we can easily store it, and we can do all that good stuff. So my belief is that the cloud is going to be that place. The cloud is going to be a very important building block for the Internet of Things. And we'll talk about this a little bit in a moment, but we've seen the cloud can be a platform from which to launch attacks. So we've seen attacks from AWS, amongst other cloud providers. But the cloud itself is also vulnerable, and we will talk about that. So we've got quite, trying to build our platform, we're trying to replicate what's in a cloud provider. We've got two very tricky criteria that we've got to take into consideration. So the first one is tenant isolation. So if I start up a VM on AWS, it's almost guaranteed that I'm sharing a server with someone I don't know, okay? It's certainly sharing a data center with other tenants that I don't know and I don't trust. So we need to provide some level of isolation between tenant A and tenant B. And we do that, everybody knows we do that with virtualization. We also have a privacy issue, a potential privacy issue, and I was having a very interesting conversation at lunchtime about this, and some legislations may be changing, but I'm going to talk about the privacy, how this might impact a botnet detector, and I think that raises some very interesting questions. So in terms of privacy, if I have a virtual environment, I don't necessarily want that cloud provider to put some kind of detection device, some kind of probe within my environment. As far as I'm concerned, that's my environment. I can do what I want to do in that. If I maybe put in antivirus software, I might be hosting a botnet. I might not want antivirus software in there. I certainly don't want a probe where the network provider is capturing my data, because who knows what they're going to do with that. They might want to sell that information to governments, advertisers, whoever. So privacy within the environment, we're talking about being able to create some sort of detector mechanism outside of the virtual environment. So over the past few years, we have started to see attacks on cloud service providers. We had a great talk yesterday about sandboxes and how malware can detect whether it's in a sandbox environment or not, but there is actually malware out there that actively looks at virtual environments, the vulnerabilities in virtual environments so that it can attack them. So we have a couple of entry points in a cloud service provider. So malware could enter through the internet, malware could enter through one of the virtual machines, and if we have a disgruntled employee, malware could enter via the LAN. So we've seen in the wild 3 types of attack. Luckily, these have only been individual attacks, and we haven't yet seen all these attacks combined. But we've seen malware going from the LAN into a server hypervisor, exploiting the hypervisor. We've seen malware jumping from one tenant VM into another tenant VM. And we've also seen malware jumping from the hypervisor back onto the LAN. So that means malware could enter our network, it could attack another tenant, or I could even run a botnet from here and maybe denial of service on the storage network as well. So clouds are going to become, if they aren't already, they're going to become victims as the Internet of Things starts to take off. So Flow. Okay, so a few of you heard of IPFIX. Probably most of you are too young to remember this, but back in the 1980s, Simple Network Management Protocol, that got replaced by syslog. Syslog was a great network management protocol for Linux environments, and it was a very efficient protocol, but the downside of syslog was it doesn't give you very structured data, so it makes it quite difficult to actually query that data. So in the late 1990s, Cisco started to look into providing alternative network management protocols, and they came up with the concept of NetFlow. The first commercial release was NetFlow version 5. In 2009, they enhanced this to NetFlow version 9, and then in 2013, the IETF took NetFlow version 9 and transferred that, made some changes to that, and made that into the standard. So the standard for network flow is IPFIX, and that can be found in RFC 7011 to 7015. So what is it about flow that we could potentially use in this type of environment? So the first thing I want to say, if we jump to the bottom of the slide, is what I'm proposing we do isn't really new. People have been using NetFlow 5 with some kind of PCAP packet information since about 2007. So if you go onto Google Scholar and you put in something like Bot Hunter, Bot Sniffer, BotCop, there's 20, 30 of these different detection techniques out there. And what they do is they're using flow algorithm or flow protocol to capture fields that they're then going to put into their algorithms. They're going to do some clustering, some correlation, and decide whether there's a botnet on the network from that information. So this isn't new. It's been around for a while. We're looking at whether IPFIX has been designed to improve upon NetFlow. Therefore, what extra benefits is IPFIX going to give us in a type of environment? So what is flow and how does it differ to things like PCAP? So everyone here, I'm sure, knows about PCAP. You've all used Wireshark. We all know that when we have PCAP, we have the header information and we also have the payload. So the fact that we have the payload means that we've got some kind of deep packet inspection or potential for deep packet inspection. So again, this goes back to what we're talking about at the beginning of the talk and privacy. The way that flow works is flow is just the header information. So we don't care about the payload. It's kind of the metadata, I guess, if you like. So we did an experiment, first of all, on our network to download to transfer a file between 2 servers. And that file was 2.9 gigabits. And we captured that with Wireshark, and that was 3.1 gigabits of data because we had some background traffic. We captured exactly the same amount of exactly the same information in IPFIX in 43 kilobytes, not megabytes, kilobytes. So for cloud service providers that have thousands of flows on their network every day, that is a massive saving in terms of storage space and potential analysis of that data later on. So in summary, we normally equate PCAP to a phone call. So between 2 people, PCAP is the content of that phone call. whereas flow tends to be equated to the phone bill. So who called who, when they did it, and for how long. So pretty much the same information, but without the payload. So, as I said earlier, Cisco invented the protocol NetFlow, and IPFIX was developed to address some of the drawbacks of NetFlow. Now, I know we have some guys from Cisco here, so I apologize for some of the things I might say about NetFlow. It's a great protocol, but IPFIX was developed to address some of the issues that we had with NetFlow. One of the biggest issues is NetFlow is proprietary. So Cisco have a version of NetFlow. Huawei have a version of NetFlow. HP have a version, etc., etc., etc. Okay, so every version of NetFlow is slightly different, and we're almost back to the old days of in the Cisco network we had. Did you use TACAX? Do you use Radius? Well, if you have a Cisco network, you can probably use NetFlow version 9. If you have a multi-vendor environment, really you need to be looking at IPFIX, and certainly the environments that we're talking about is going to be multi-vendor. So IPFIX gives us vendor neutrality. IPFIX is also extensible, and what that means is you can create templates for what you want to capture. So the way that NetFlow version 5 works is you have a NetFlow exporter, and that captures the packet, that takes field information from the template information from the headers, that converts it into NetFlow or IPFIX, and that sends it to a collector somewhere else on the network which stores this data, and we analyze that data after. So NetFlow version 5 had a fixed template. It had 18 fields in this template, which included things like source, destination IP address, ports, protocol numbers, whatever you'd expect within a packet header. But it also had stuff that you may not necessarily want to use, like VLAN ID, class of service, those kind of things. And because NetFlow version 5 is fixed, you capture this information whether you want it or not. Okay, so you have, for every single flow, you capture a 48-byte PDU, which doesn't sound like a lot, but again, scale that up to several million. You've got potentially a lot of wasted data there that you're capturing because you have no choice. So NetFlow version 9 decided that that they would add some kind of ability to create some templates. So you could start to choose from 79 different fields what you could actually capture. And IPFIX took that one stage further and said, we've got 433 fields that you can capture. And guess what? If there's anything else you want to capture as well, you can write plugins to do that. So IPFIX has a lot more flexibility in what you can capture to report back, to analyze for the data. NetFlow runs on UDP, whereas IPFIX runs by default on TCP, but it also includes a lot of things, good things like stream congestion control and those kind of things as well. So it's a more robust protocol. NetFlow wasn't designed, when NetFlow was designed, they didn't really take any security into consideration. So IPFIX has been designed with security from the beginning. So that includes things like data obfuscation, which NetFlow doesn't have. So if you're sending stuff across a network, there is a potential that someone can intercept that packet, sniff that packet, or change that packet. With IPFIX, we can encrypt the packet so we know that what's being sent, we hope what's being sent at the other end is legit. And also, IPFIX offers next generation support such as IPv6, MPLS, multicast, etc. So at the want of upsetting the Cisco guys here, NetFlow 9 does support most of these things, okay? But as I said earlier, NetFlow 9 will support them in a proprietary mode. We're talking about supporting this as an open standard. So we started to set about building our data capture elements, and just to be clear, what we're trying to do is emphasis on the data capture. Okay, I mentioned earlier there's all these experiments. If you go onto Google Scholar, there's a lot of academic research using NetFlow version 5. They have their own algorithms for detecting botnets. Okay, we're not actually looking at creating an algorithm. We're just looking at the data capture mechanism, and then we'll feed that into some kind of algorithm at a later stage. So all we're talking about now is capturing a technique for capturing that data. So we wanted to build this system using off-the-shelf equipment as much as possible, and we wanted to keep it open source because we might need to write some code to link various bits and pieces together. So keeping it open source would allow us to do that. So in order to sort of create a cloud provider type environment, we had to pick some kind of hypervisor to run our virtual environment on, and we also looked at software switches as opposed to hardware switches. So we had a bunch of hypervisors that we could have used. We looked at all of them, and we decided to go with Zen in the end, Citrix Zen, because it's open source, but it's also quite a common hypervisor in cloud providers. Certainly used in Amazon AWS. It's within the OpenStack, it's within Cloud Stack. It's used quite a lot in this area. Likewise, with the open switcher, with the software switches, we had various choices that we could have used, and we decided to go for Open vSwitch. It's open source, it's clues in the name, and it also sits very well with Zen hypervisor. So where you see Zen, you tend to see Open vSwitch. So that's the reason for choosing those two for our platform. Okay, so we started to build the platform, and as you can see, this is number one. It wasn't quite as easy as we thought it was going to be. So first of all, we went to Citrix and we downloaded a copy of Zen Server, which includes CentOS operating system. It includes a Zen hypervisor. It includes a GUI for creating or destroying or migrating VMs. And it also includes Open vSwitch. So everything we wanted in one package. We set that up on a server. We put Zeus into one VM. We infected another VM, and we managed to see the infection process and the keep alive processes and any data transfer between the two VMs in NetFlow version 5. Okay, that was easy, simple. Get my PhD done within a week at this rate. Little did I know. Okay, so there were some issues that we hit. Zen Center, the GUI for Citrix Zen Server, doesn't support IPFIX. Okay, that's not really a massive problem because there's a command line we can use. In order to run Open vSwitch in order to run IPFIX on Open vSwitch, and what we're doing here is we're having the switch acting as the exporter, so the switch is capturing the data, putting it into an IPFIX packet and sending that somewhere else to our network to be analyzed. We needed version 1.10 of Open vSwitch. It ships with 1.4.6. Okay, some more upgrading to do. We can probably cope with that. Not a problem. The problem that we did have is Open vSwitch version 1.10 requires 64-bit CentOS operating system. Zen Server ships with CentOS 5.5, 32-bit. Okay, another upgrade. That's when we start to hit problems. Okay, out of the box, Zen Server, the DOM0 ships with 4 gigabits capacity. 3.8 gigabits of which is Zen, 0.2 gigabits which tends to be the CentOS OS. So it doesn't leave us with a lot of room to do some operating, so some upgrading. So, hands up, I'm not a Citrix expert. Maybe some guys from Citrix could have upgraded this, but there was no way I could upgrade CentOS. And 5.5 is an old version. I think CentOS is now on version 10 or something like that. So this is an old version. I could not get this upgraded. Okay, PhD is not quite going so well now. Right, so about a year down the line, Citrix released a new version of Zen Server, version 6.5. So it runs on a CentOS Linux OS, 64-bit. Brilliant, that's what we want. We have Zen Hypervisor, 64-bit. Again, another massive tick. And it also comes packaged with Open vSwitch. So really everything that I want in one package. My prayers are answered. Great, I can start collecting some data now. Because version 2.1.2, Open vSwitch supports IPFIX. So they said. Okay. What it doesn't support is aggregation and timestamps. So when you capture IPFIX data, or NetFlow data for that matter, one of the benefits of using it is aggregate similar flows. So if you have flows that all have a similar IP address, similar port address, or whatever, they aggregate those into one flow. What IPFIX was doing on Open vSwitch was it was doing for every single packet it was sending an IPFIX flow. So we were getting thousands and thousands and thousands of flows. Also, these flows had no timestamp, so I couldn't actually picture what was happening on my network. I just had a load of data, load of data transfer. I didn't know what was happening or when. So, okay, we've got another problem. I'm not an Open vSwitch expert. I spoke to Open vSwitch. They said it works. I said, no, it doesn't. They said, yes, it does. I said, how? They said, talk to somebody else. Great. OK, so I couldn't get it to support Open IPFIX. So we went right back to the drawing board, and we had Mark's bespoke build version 1.0. We had an operating system that we actually know how to use. OK, CentOS didn't even include the yum command. OK, you had to download everything manually. I've got apt-get installed now with Ubuntu. I know what I'm doing. We went to the Zen project, which is a standalone version of the Citrix Zen hypervisor, and we downloaded 4.4. That comes with a fairly basic tool API, so we downloaded something a little bit more useful, the Zappy tool stack. We also downgraded Open vSwitch back down to version 2.0.2 because we're not going to use Open vSwitch now to export the IPFIX data. We're going to use Open vSwitch to do what it's supposed to do, virtual switching. So we downloaded whatever was available on the website at the time, and that was 2.0.2. So now we need to have some kind of probe on our network that's going to capture the data, export the data to a collector somewhere else on our network. And we looked at a whole different bunch of probes, and two probes stood out, NetProbe and a product called YAF. And we decided to go for NetProbe simply because it was the easiest one to use. Okay, it has some other benefits as well, but to create an IPFIX template, NProbe stood above everybody else. It was dead simple to use. So here's the cloud stack that we created. As you can see, it supports NetFlow 5, NetFlow 9, and IPFIX, so we can start to do some comparison between the different protocols. And it also, within our stack, we put something on there called Neo4j. Anyone use Neo4j? Yeah, OK, good. So that's a graph database package, and I'll talk a little bit about that later on. So this is showing us an example of a server where we have a bunch of virtual machines in user space. Open vSwitch sits between the user space and the hypervisor. And we also have a probe. Now, this probe could be anywhere, but what this shows here is this probe is not within the virtual environment, which is one of the criteria we set out to try and achieve. And we'll talk about probes now. So a simplified network of a cloud provider, and the PCs in black are potential places we could put our probes. So we can put our probes within the tenant virtual environment. We could put our probe on the network. We could hang our probe off a device such as a server, or we could even put it on a firewall or the IPFIX collector. Wherever we wanted to choose it, there's multiple places we can put this probe. So we wanted to find out how can we create the least number of probes with the maximum visibility, because the more probes you have to start coordinating all the probe data, and also the probes themselves are open to attack. So if we've got more probes, they could potentially become a victim of attack. So we've started off, even though we said we're not going to do this, we wanted a baseline, and we said, let's put the probes in the tenant virtual environment. So what this diagram is showing is the red lines are successful pings, so pings between this device and this device, this device and this device, but it's red because the probe wasn't picking that up. Okay, so put a probe in the VE, in the customer's virtual environment, we saw no data at all on the network. Can anyone guess why that might be? Okay, well, it works in the same way as Wireshark. We didn't have these networking interfaces in promiscuous mode. We weren't using any span ports, any mirroring ports. So unless the IP address, source or destination address, was to one of these probes, we weren't seeing that traffic. Okay, so we moved the probe out of the virtual environment, put it on the LAN. Again, exactly the same thing. We might have more control over putting some of this equipment into promiscuous mode where we probably don't have in virtual environments, but out of the box, we're not capturing any data by putting our probe on the LAN. So we've got a bit of a problem. Again, another problem. We had a few problems. So we thought, well, what about the Open vSwitch sits between the user domain and the hypervisor domain. What about if we installed the probe on top of the hypervisor so that it's sitting right next to Open vSwitch. Open vSwitch will then send any information to the probe, and that's what we saw. We saw that the green lines are showing pings that we successfully picked up in the probe, and as you can see, because every packet is going through our server with Open vSwitch on, we had good visibility of data across the network. With our probe on one server, what we don't see is traffic in another server. We talked earlier, we talked at the beginning about malware that might be able to jump between VMs. We can see that traffic between VMs because it's going through this server, but if these two guys are talking to each other, we're not going to see that because we don't have a probe on that server. So we went to the extreme of putting a probe on absolutely everything, and we got full visibility of the network. But as I said to you, we don't want to have an overkill on probes. So for this, since for our environment, we've left the probes out on the LAN. We've kept the probes on the server. We have no probes within the virtual environment. So actually, we are seeing traffic coming within a virtual environment, between a virtual environment, or from a virtual environment out onto the LAN. So yeah, we were able to show that installing our probes on top of the hypervisor gave us maximum visibility of traffic. Okay, so that's most of the work we've done so far has been setting the network up and getting these probes in place. What we're looking at now is what can we do with this IPFIX template in terms of botnet detection. So we've managed to get something like, we've analyzed something in the region of 10 million packets, which equates to about 1.5 million flows, and using some kind of some statistics and some correlation, we've come up with what we believe is the minimum template. I don't know if you can see that, it's quite small, but the minimum template for the information that we need to capture on the LAN to be able to recognize a botnet. So it's flow start times, flow end times, some information about bytes. Interestingly enough, our data said we only need destination IP address, not necessarily port IP address, but we need both port and source and destination ports, and also protocol. So, and also the direction of which the traffic is going. So that is an absolute minimum of what we need to capture. Now, the PDU size of this works out as 22 bytes. I said earlier that NetFlow version 5 works out as 48 bytes. So we can capture pretty much the same useful information in less than half the bytes. Okay, but what you will notice on there is that this is just traffic information. There's no PDU information. Yeah, and hands up anyone in the room that thinks we can detect botnets without HTTP or DNS. I don't think we can we? Okay, I'm going to skip that one. Sorry, Adrian. We'll come back to that if we have time. Okay, so I mentioned Neo4j earlier as a graph database package. So what we've managed to do is replicate the traffic communication within graph databases. Now, graph databases are used a lot in network security. I couldn't find a lot of work about using these to visualize botnets. So we tried it on botnets, and what we can see here, it's a very simplified view, but we had a server in gray here, and this is the communication between the other devices. So if we look at this picture here, something's going on with PC7. Lots of people are talking to the server, as you'd expect. PC7, as far as we know, is a normal PC. Why is all this traffic going to that device? As it happens, we had Zeus command and control center in there. That's why everybody else was talking to it. Now, if we narrow that down, start looking at different protocols, if we look at HTTP, we can represent the amount of traffic. The thicker the bar, the more traffic. So now we get a better picture that, okay, there's a lot of HTTP traffic going to this device. I'm not saying that this is a botnet. I'm not saying that's it, shut that PC down straight away, there's a problem. I'm saying at this stage is we've got some intel, that might be an interesting device to go and look at. So at some stage we need to implement some kind of algorithm, and what graph theory will allow you to do is look at the number of nodes coming in, the size of the nodes, and start comparing them with signatures. So that's future work, and that's something that we've started to work on, and I think it's quite an interesting way of actually displaying the data that we're capturing. Oops. Okay, so I think there's very interesting questions been raised around this research, and it's the kind of the concept of privacy. We decided at the beginning by using flow protocols that we'd sacrifice the payload for privacy of the tenant. Now, of course, whenever you sacrifice a payload, that comes at some kind of cost. Okay, so I said this earlier, can you detect botnets without some kind of packet information? Probably not. What IPFIX allows you to do that NetFlow doesn't allow you to do is to create your own plugins to take information out of the packet that may not necessarily be within the standard template. So we've developed an IPFIX extended template, if you like, that can capture HTTP, DNS, SMTP, IRC information. If there's something else you wanted to capture, we could probably write a plugin to capture that as well. But that kind of comes at the cost of privacy. You know, we've said the tenant doesn't want a probe in the network. Okay, we put our probe outside the network so they don't need it. But also, the tenant could potentially question, why are you capturing my information anyway? Do we tell them that we're going to capture that information? Does the cloud provider state that in their terms and conditions that we may capture the certain HTTP GET information or DNS information at the benefit of providing them with security? I don't know what the answer to that is. You know, I'm developing this tool. The tool can provide this technology, but we've got some issues, some regulations to sort out around privacy, and I think that's potentially a whole different debate. But that issue is there. This slide, for those that can't see it, is showing our extended IPFIX template. So we have 4 DNS parameters that we're capturing: ID, TTL, query name, IP address, and a bunch of HTTP parameters as well. So, you know, you could say that HTTP GET, HTTP referrer, IP, DNS IP address, DNS query name, that's quite intrusive traffic that we're capturing there. But the technology will allow us to do that if that's what we decide to do. So using a combination of this template and the other template that we've written, we should be able to capture significant information to detect botnets in the environment that we're looking at trying to detect them in. Which brings me on to testing my network, and I'm not proud, I'm going to start begging in front of everybody. I've tested this with a really old version of Zeus. I've also tested this with SpyEye, but I really need to test this now with ideally something like Game Over Zeus, some P2P botnet, an IRC botnet. So I'm reaching out to you guys, and if you've got, bear in mind I need the builders, not just the executables. If anyone can help me here, happily reference you in any of the papers that I'm writing and the work that I do. So please, if you've got anything that can help me, let's talk tonight or whenever. So, conclusions. I think we managed to create an IPFIX traffic capture mechanism using off-the-shelf technology, eventually. Cloud service providers, about 80% of cloud service providers already use Flow in some form or shape, be it NetFlow 5, be it NetFlow 9, be it IPFIX. So this is not new technology to them. This is technology that they're already comfortable with, or at least they should know a little bit about. We've also shown that if we put the probe on the hypervisor, we get good visibility of traffic. And we've also created what I believe is probably the first IPFIX template for botnet detection. I'll stand corrected there if anyone knows otherwise, but I haven't found any information that says that there's anything out there. So, you know, I still have a year to go. I've still got a whole bunch of testing to do, but you know, hopefully I think I've made some nice progress. Who cares? What does this mean to anybody? As I said right at the very beginning, clouds are going to host the internet of vulnerabilities. They are going to host smart cities. The cloud is a platform. We've seen it being used as a breeding ground for botnets. So it's already a platform for attack. It will be a platform of itself being attacked for attack on storage, other tenants, or in virtual environments. So hopefully what we've created, it's by no means the end tool. It's by no means the only tool, but I think it's at least a step in the direction to look at detecting botnets within a LAN environment. And let's not just leave that just to cloud service providers, but we take a campus like a university, this probably has a similar application in an environment like that as well. And that's me.
Okay. Any questions?
Stunned silence.
Over there.
So is this listening on? Yeah. So you seem to have built a somewhat heavyweight, I guess, system for doing your experimenting. Did you look at using any simulation tools like NS2 or Botnet or anything like that, where you have complete control over network infrastructure and people have already built simulations of malware networks such as peer-to-peer networks and stuff like that, which would allow you to quickly perform your experiments in a controlled environment and scale it up as much as you want to?
Yeah. Okay. The easy, simple answer to that is no, we didn't. We wanted to actually, rather than simulate, I mean, I don't need to tell you guys that botnet research is pretty difficult because you often need the builder as well as the sample. So it would have been a lot easier to simulate a network and maybe simulate a peer-to-peer botnet over the top of that. But we actually wanted to try and physically build something something tangible that we can use off-the-shelf information, use real equipment, use real-world equipment, and try and actually build something physical. So good question. Yeah, that could have saved us a lot of time, but the end goal, if you like, was to actually have a can I say real detection system at the end of it. So no, we didn't. Is the short answer to that.
Another question. No more questions? 1, 2, 3. Okay. Thank you, Mark.
Thank you.